All right, here is 3.1, first lesson of chapter 3. Topics for the chapter are exponential and logarithmic functions. Okay, that means both working with their graphs and their equations. Today the focus is just exponential, and you'll kind of see that really if we do that, there's only two things we can really do. Well, there's more, but there's really only two things that we're gonna do, which is to kind of produce some basic sketches of graphs and do some application problems that really just involve evaluating, which again is a fancy way of saying, plug in an x value to get an answer. All right. I want to make that point now that to do more, fancy, sophisticated stuff with exponential models, we need logarithms at some point in time. So there's only so far we can take it in section 1. Let's kind of start with defining an exponential equation in terms of what they look like. I'm going to deviate from the book just a little bit. Mine is going to be not more complicated, but a little more thorough. A times b to the x power if you see that value for a, we're going to call that our starting amount. And then b, which is like the base of the exponent, and that's a good point to bring up here, that this is what makes exponential functions unique, is that x variable is up in the exponent, right? Up in the exponent. The base is what we will call our growth rate. A couple rules about b. Really just one major one. B can't be 1, okay? If it's 1, then it becomes a really simple linear model, which we don't want. That's not, it's going to be a straight line and not the exponential curve that we're looking for. If b is bigger than 1, you're talking about growth. If you're doing applications, it's very, very rare. I guess b can be negative. I'm not really going to go there yet with you. So if it's between 0 and 1, then you're talking about a decay model. Okay? And we can use those terms because one thing exponential functions cannot do is change direction. Okay? They can't do it. So if you have a growth rate that's over 1, you're talking about a function that's going to be increasing all the time. If it's between 0 and 1, it's going to be decreasing all the time. Today you'll see both. Okay, let's talk about a little bit in terms of graphing. Nothing crazy going on with these. Both are going to be growth models. And the other one here will be 4 to the x power. Okay. I'm just putting a set of axes on both of these. And then a good place to start with the graph is a table. Nothing super crazy in terms of the x values. -3, -2, -1, 0, 1, and 2 for 4 to the x power. Let's do the same. This could be a point to pause for you. Again, if you feel like you could produce these graphs without any assistance, go right ahead. You could pause and then check your work. All right, so over here, if I start with the positive ones, I put in 2 for x, and 2 cubed is 4, 2 to the first is 2, 2 to the 0 is 1. And as I go backwards, notice that each of those y values are being divided by 2. I bring this up because when you put in negative values, sometimes things can get a little funky because you get some weird answers. As I get to these 3 negative values, this pattern should just continue. Okay? So 1 divided by 2 would be a half. Divided by 2 again, it would be a fourth, an eighth. As I go negative, those values get really, really, really small. Okay? Now before I plot them, let's go over here. 4 squared is 16. 4 to the first is 4. 4 to the 0 is 1. Keep dividing by 4 as I go back to the negatives. 1 over 4, 1 over 16, and then 1 over 64. Okay? I'm just plotting these points. And you can see the beginnings here of a nice exponential curve. And again, that's 2 to the x power. Okay? 4 to the x is going to look really, really similar. Over 16, 1/4, 1. However, look at how quickly it increases. Okay? They both look pretty similar because they're both growth models, but you can make that growth rate bigger, and you're going to see that the rate at which your function is going to increase, it goes up quite a bit. Just take a look at this. Okay? By the time the x value was 2, this one had only increased till about to 4. This point in the table right here. For 4 to the x power, by the time this one had an x value of 2, the y value was already up to 16. Okay, so it increases quite a bit quicker. All right, let's look at some transformations. Okay. And let's see here, the function that I want to look at, because if we're going to talk about transformations, we need a parent function. So let's say our parent function is, let's go right in between those other two. Let's keep a positive growth rate. So let's say that it's 3 to the x, and now here's what we're going to do. First things first, and these are just going to be sketches. Okay, so I'm not going to do a table of values. Or anything like that. Okay, I'm just going to put that on there and then say, all right, right? Looks good. It hasn't been shifted. It hasn't been stretched or transformed. It just looks like a really basic exponential growth. That's all we need to see in our sketch. Okay. Now I want to just show you how transformations show up in exponential equations. So I want to look at 4 of them. So So again, each of those are just rough sketches of 3 to the x. Now I'm going to switch over to blue, and here I'm going to have some transformations. And let's do 3 to the x plus 1 power. That's one I want to look at. That's a shift. A little hint on that one. Actually, so is this one. 3 to the x minus 2. Oh, and then negative 3 to the x power. And then here, 3 to the negative x power. Okay? Now, it's been a long time since we've hit transformation, so it's good to see them again. This is a shift. It's up there with the x variable, so it's horizontal, but the x is always funky, and it does the opposite of what you would think. So it's shifted 1 unit to the left. Okay? Again, what I really want you to see is that if in an exponential equation, for the horizontal shift, that's what you're going to see, is you're going to see something added or subtracted in the exponent. Okay? Whereas here, if it's at the end, this is now vertical. And it's shifted 2 units down. And would look something like that. Okay? Negative signs are always reflections. It's a matter of over which axis. Okay, there's a negative sign out front. Which is going to give you a reflection over the x-axis. And now if you put that negative sign up in the exponent, that would be reflected over the y-axis. That's a big thing to see that negative sign up in the top of, up in the exponent, because if you put that up there, notice the 3 to the x was a growth model, and then it switched to a decay model. So there are a lot of cases where if you see that negative sign, that's a big indicator that it's significant about what the graph is doing. And again, that's why we want to look at these transformations, so that when you see just an equation without a graph, that you have as good a sense as possible as to what's going on. All right, I want to talk about the natural base E. Okay. When we covered this in class, we did a little investigation with it, and it was really this. I gave you kind of an interesting little function. It was exponential, but it looked like this. And I gave everybody a really open-ended question. I wanted them to tell me what happens to the y variable as x gets really, really big, right? Which leads into the question of, well, what's a big x value? And, I wouldn't tell anybody. Maybe 5 is big, maybe 10, maybe it's 1,000,000. Cool thing about the number line, never ends. So whatever x value you put in, you can always put in a bigger one. Okay? And then everybody put on the board kind of what their best guess was as to what's happening. And what we saw that's about as far as anybody got, is so the y value gets bigger to a point, and then it stopped getting bigger, and it hit this limit, okay? And that is our first look of the year at base E, okay? And the thing you really need to know about it is if you're doing an exponential model that uses the keyword continuous, you're talking about a model that's base E. Okay, that's what it's used for. That's, if you're writing the equation, that's what you got to know. You'll see a lot of other problems that use base E, so you should know it when you see it, because it's a big, big part of exponential functions. So down here, we're diving into some applications, all right, that now kind of illustrate the difference. Okay, if we're talking about a compounding period, okay, this relates really well to interest problems. The amount is going to be your principal. You've got your rate over how many times interest is compounded to the n times t power. Okay? So our first one tells us that our $12,000 investment, it's going to be compounded quarterly. So this is the number of times that our interest is added to our principal. Okay? If we're the one doing the investment, you know, having invested the money, the more often the better. So this is saying that the interest will be added to our principal 4 times a year. So R needs to be 0.09. That needs to be split up over 4. And you'll notice on all these, T is always, always, always in years. Okay, largely because your interest rate is per year, which is why it has to be divided by 4. Okay? Over those 5 years, we would see some good growth. Over $6,000. You get something like that. Okay? Part B is going to take the exact same approach, but now the interest is going to be compounded monthly. So there's not going to be a whole heck of a lot that's different here. It's really the same formula, except now, instead of n being 4, n's going to be 12. And the investment is still for 5 years. Okay? The significant thing, though, is down here. It's not, super different. How different it is would depend on the numbers. Okay? But we do see, as far as the end amount from our investment, we gained a little bit more. Okay? Like $62 more. Okay? So the more often the interest is compounded, the more we're going to make. Okay? Which leads us to part C, where we have to use a little bit different formula because we see that it's continuous. Now this is going to use a slightly different formula that some people like to call PERT. Principal is still the same, but continuous means we have to use base E. Okay? Check your calculator for a button that's base E. It has one. But then the interest rate goes up top, and we have 5 for T. Okay? So if it's continuous, that's a big thing to identify because the structure of the equation is a little bit different. Base E and the rate needs to go up in the exponent. Now this is kind of like interest is being compounded all the time. So you can see as far as the end value of the investment after 5 years, it's even a little bit better than part B. Okay? Because again, this represents the case where interest would be compounded constantly, continuously, like it's going on all the time. All right, one more application problem, which again, we can't do a whole heck of a lot other than just kind of taking a model, plugging in an x value to get a y value. We just can't at this point. This is a half-life model. And I just want to point out a couple things. 10 is your starting amount. We've obviously kind of switched topics here. We've gone from money and growth of investments to, plutonium and nuclear accidents and radioactive decay. So definitely a new context here. we're saying if we had 10 pounds of plutonium, how long it would take for it to basically go away. And it's not very quickly. 10 pounds is the starting amount. Notice the base is 1/2, so it's a half-life problem that involves exponential decay. 24,100. We have T over that. That number is always going to be the length of your half-life. Okay? So keep that in mind. Half-life for plutonium seems long. You know, I don't know how it compares to other substances, but 24,100 years seems long. We're just going to use it for two things. Okay? The Chernobyl accident was in 1986, so let's say 10 pounds of plutonium, you know, was spilt, or, you know, from the explosion went out into the air. I have no idea how much. My guess would be more than 10 pounds, but I really don't know. How much of the plutonium is left in 2010? $24, because this is 24 years after the accident. 24 years have gone by. How much plutonium is left? That's an expression that just needs to be plugged into your calculator. And you would see most of it, okay, 9.993 pounds. Remember, what this model is saying is it's going to take 24,100 years to have 5 pounds of plutonium left. That's how long it's going to take for half of it. Okay? So yeah, after 24 years, seems like a long time, but hardly any of it's gone away. Now the second part here is a little bit of a different story. It now asks us how much is left after 100,000 years. Okay, now before I plug that in my calculator, I'd look and say, all right, 24,100 years is what it takes to get rid of half of it. Okay? 100,000 years, that's a lot more. So half would be 5. I'm expecting that there's a lot less than half left. A lot less. You know, maybe a pound, maybe 2, something like that. I'm expecting something closer to 0 than to 5. Okay, kind of based on what I know about the model. Sure enough, when you plug that in, 0.564 pounds is what would be left, a little over half a pound of plutonium after 100,000 years.